Hello everyone, my name is Siddharth and I would present some of our results on using green nanomaterials for environmental decontamination. I would like to thank the workshop organizers for giving me this opportunity. So the outline of my short presentation is going to start with group's vision. Then I'll give you three examples where bio-inspired silica has been used for environmental remediation. So what we've identified is that current nanomaterials production is unsustainable and limited by the product quality it can achieve. And therefore, inspired by nature, we are developing strategies for discovery, design, and sustainable manufacturing of a range of green nanomaterials. The focus in our group is on demonstrating potential applications in the real world for green nanomaterials, and some of them are shown in this schematic on the right-hand side. Of course, environmental remediation is one of the key applications. We're also looking at increasing the technology readiness levels, in particular by focusing on scale up and manufacturing of these materials. And finally, developing technologies that are ready for commercialization. Okay, so let's jump into environmental areas. So the first application I'm going to talk about is the dye removal from water using our green nanosilicas. And quickly showing you the need for that. As you can see from some of the numbers noted on the left-hand side, it's an important problem. And while there has been some focus, there are two issues. One is that predominantly most research work is focused on azo dyes, but hardly any on anthraquinone dyes. And secondly, most technologies are not suitable for environmental remediation at scale because of either cost or other issues pertaining to the technologies used. So we've used our functionalized green nanosilica, and we studied the dye removal kinetics. And what we can see from this graph is the amount of dye adsorbed as a function of time. And we can see that modeling the kinetics through Weber and Morris model provides a really nice description of the behavior. In particular, this model also enables the understanding of the mechanisms, which tells us that the absorption is predominantly governed by chemisorption and it is limited by intra-particle diffusion. So doing other work, we've also figured out what is the mechanism in terms of the adsorption of these materials. So we've taken two kinds of materials with differences in functionalization, which is shown by the red lines here, and the blue circles are showing the pollutant. We've also done adsorption isotherms and tried to model them to understand the capacity and behavior. And we can see that two classical models have been applied, while only one of them fits for one of the materials, and the second one can be fitted by both models. We can extract the capacities of bio-inspired silica and compare them with other materials, and what we see is that these are really highly performing systems. So we have highest adsorption capacity, rapid adsorption under acidic conditions, and we have a really good reuse potential, which I haven't shown here, but you can explore that further in detail in this publication. Moving quickly on to a second application of arsenic removal from contaminated waters. And in this case, we've used a strategy of functionalizing green silicas with iron. And iron is known chelating agent for arsenic. And as we all are aware, arsenic has severe health issues, and it's also been categorized as a group 1 carcinogen. So similar to the previous example, we've studied and modeled the adsorption behavior. We've also found out that the porosity of the materials and the content of iron in the system is really key in its performance. So we tried to connect the extraction efficiencies with the porosity and also the iron content. Looking through dynamic systems as they would be in the real life operation, we've seen that the extraction efficiency is extremely high and it remains high, and that these materials can be regenerated and reused, which is an exciting avenue for real life implementation. When we compare the kinetics and the adsorption capacity of our materials with other existing reports, we can see that our materials really outperform in both avenues combined together. Finally, briefly, let's look at the use of these materials for VOC removal. And again, the strategy has been identifying the right functionalization of these materials. So we've been focusing on monoaromatic hydrocarbons and formaldehyde as they are the key indoor pollutants. And as we're spending more and more time indoors with tighter end buildings for energy efficiency, the influence of these contaminants is causing a big concern, especially because they are categorized as carcinogens. So briefly looking at some of the results, the extraction efficiencies of these materials for toluene, ethyl benzene, cumene, and dichlorobenzene was studied, and it's extremely high, especially when compared to a benchmark mesoporous material called MCM41. So we have found out that these remarkable extraction efficiencies and selectivities arise from a unique combination of porosity, in particular pore size distribution, the disordered nature of the pores, and the availability of meso and micropores for transport and adsorption. With that, I would like to end my presentation and happy to take any questions during the workshop. And thank you very much.